Well, hello, physical geology students. We're going to go and do a brief survey of orogeny. Now that we've talked about plate tectonics and we've talked about igneous rocks, we've talked about volcanoes, we need to talk about rather than focusing so much on the trees, let's talk about the forest a little bit. In other words, we've talked about how we produce mountain ranges, and we've alluded to the different kinds of mountain ranges that exist. We've talked about how igneous materials and intrusions can form volcanoes. But really, when we're talking about plate tectonics, we're talking about large-scale events that are occurring that are much bigger than the naked eye can see. If I look at this mountain here, this is in Montenegro, southern Europe, southeastern Europe. If I look at this mountain here, I don't have any information about it other than the fact it's an individual mountain, one of many mountains. But unless I know what I'm looking for, tectonically, I'm not really sure what to say about this. So when we look at an individual mountain, in other words, there's not a lot. There's information there, but when we look at the mountain range in terms of its overall shape and in terms of the way that the mountains arrange themselves, we get a lot of information that tells us about the plate tectonic situation and so forth. So let's take a look at this. By the way, if I ever get a chance to go and visit this place, I will take it. Looks awesome. There's a monastery down here. All right. So orogenesis, we should just define this. And this is really the only slide where we're really going to have any text because, again, we've dealt with a lot of this before back when we talked about deformation and so forth. So orogenesis is an event, quote unquote, because it's a geological event. It takes a long period of time that leads to structural and compositional changes in Earth's lithosphere at plate margins. Plate margins, of course, being the three types of boundaries: divergent, convergent, and transform. Structural changes, we've talked about these. These are things that these are forms of strain that result from the stresses placed on rock at these boundaries. We haven't talked as much about compositional changes. We'll get into that more next week when we look at metamorphic rocks. But these events can last a long time, on the order of tens of millions of years in many cases. And in fact, of course, the effect of these events is also very long because the mountains tend to stick around for a long time. So the Appalachian Mountains the Alleghenies that you see out to your west, they were formed 248 or so million years ago when Pangea was formed. And of course, they had at one point eroded down to a peneplain or a plain, or they were essentially gone. But the core of those mountains was uplifted again through a rejuvenation event that occurred during the Cenozoic era, which may have been an upwarping of material or pushing up of material from the mantle and so forth. It's hard to say for sure exactly how the Appalachians came to be as they are as you see them today. But still, these mountains have been around for a long time. And they have a particular form to them. So these are folded mountains. We'll look at those more in a minute. There are also fault block mountains. Mountains that are bounded on one side by faults, either because of stretching through normal faulting or compression, reverse faulting. And then volcanic mountains and dome mountains. And there probably are some smaller subcategories of mountains that we're not going to cover here. But the main thing is to sort of get the main categories out there. So let's look at fault block mountains. These tend to be either lifted or sloped mountains. The lifted mountains, as you can see down here actually, are typically the Horst and Graben structures. We've looked at a fairly decent amount. So we've seen these in the Icelandic Thingvellir Rift Valley. You've seen these now in images taken from East Africa, the Red Sea, and so forth. I also want you to think now about the basin and range of Nevada. Another example of a fault block mountain is one like this, where you have thrust going on. So fold and thrust mountain belts, which actually the Appalachians are kind of an example of as well, where you get the folds, you get these linear folds, and then they eventually, some of these folds will break, and you'll create an actual thrust fault situation where material is thrust on top of the same material. So these are broken apart, right? So you start flat and you begin to fold it, you fold it over, and then you break it. And then after it's broken here, the top part of this then slides on top of the bottom part of this. We call that a thrust belt or a thrust fault. And that's what you have down here, number 5. So Here in Death Valley, California, another example, yet again, of a horse and graben structure, essentially, where you've got a horse over here and a horse over here, the graben in the middle. Death Valley is just a series of, just one of a number of such valleys in the basin and range throughout the state of Nevada and California that form these large linear valleys, look like little caterpillars crawling to the north here. But you got the Great Valley of California, which is part of the ancient basin and so forth, and then you've got all these little areas that are a result of stretching and thinning of the crust, and of course normal faulting. But you can see they have a particular shape to them. They have a nice sawtooth ridge across the top of them. They will typically, if you get very close, they'll have a fault scarp on one side, and then a very flat valley on the other where deposition is occurring. Another basin that you don't see quite as easily actually occurs right here in Virginia. It's called the Culpeper Basin. It's one of the many Mesozoic basins that exist along the East Coast that are the result of Pangea ripping apart during the Triassic. So these are Triassic in age and contain Triassic sediments as well as Jurassic igneous materials, bounded on both sides by crystalline basement complex rocks. So here is where the Culpeper Basin is, in this blue and red area, in this Triassic basin. You can see where an exposed rift, as an exposed rift basin, what it would look like here on the surface. There are undoubtedly in the coastal plain area buried rift basins, and then you perhaps offshore rift basins before you get out to the Atlantic Ocean. But all these sediments are, of course, covering it on the coastal plain. This one happens to be exposed, and there are a couple others further south in Virginia, and then of course up into New Jersey and places like that, New York and New England. But the Connecticut River Basin, for instance, is another example of one of these. But this is where the only dinosaur footprints or evidence of dinosaurs in Virginia has been found in the Culpeper Basin, which happens to have the right age sediments. But on one side you have the Blue Ridge, on the other side you have the Piedmont. So while there is certainly a horse and graben structure there, it's more difficult to see because the Piedmont and the Blue Ridge are much more eroded than, say, in Death Valley, where you can clearly see the horse on both sides upraised over the valley. All right, and of course, out in the Grand Tetons of Wyoming, where you get this really dramatic view, and of course of the mountains, where you've got this very, very sharp fault scarp down at the bottom here of these mountains because of the Teton Fault and the stretching of the lithosphere in this area. So you get this, of course, Yellowstone is up north this way, but because you have this area being uplifted and this area being dropping down because of the stretching, you get this really dramatic fault scarp like that. Okay, folded mountains. Getting away from fault block, looking at folded mountains. You guys live amidst folded mountains, and so this is something you should be pretty familiar with. If you look at the Shenandoah Valley from as an aerial shot, you can see here the valley over here, Fort Valley over here, the Massanutten Mountain Range on both sides, and you can see these nice linear mountains, which are the result of the folding. Now, this Massanutten Mountain happens to be inside of a syncline, so the rocks dive underneath here and come back here and then come back on this side, and these ridges are actually formed because they are lined with sandstone. If you go up onto the ridges, you'll find nothing but sandstone up there. The Martinsburg Formation, the shale that a couple of you are looking at, tends to be right along the base and along where the river is. The river actually is defined; its meanders are defined by joints and bedding planes within the Martinsburg Formation. Then out here in the valley, you have the Ordovician limestones. So we actually have a situation where there's a syncline here, and where over the valley is an anticline. But you can't see the anticline anymore unless you know what you're looking for. But that's what we call a folded mountain range. And basically they get crumpled up. It's a crumpling up of lithosphere as convergence occurs. Another example, of course, this classic image of an aerial shot from the Pennsylvanians. This is part of Pennsylvania, where you see the Appalachian Piedmont, the Atlantic coastal plain down here, and the Appalachian Plateau, further northwestern Pennsylvania. But you can see the folded belts of mountains through here. And of course, they tend to look like this, with sequential ridges one after the other because of that folded nature. Yeah, okay, so here's the folds. There's one more image I was thinking of, and it's coming up next, actually. It's this one here. But you can see the folds. Here are the bedding. Here are the beds diving beneath. So you can imagine that the geologic map on top looks like a bunch of lines, parallel lines of both here. So the Glenshaw Formation, in this case, will run up this way, north and south on the surface, and of course the same thing over here. And it'll be parallel or mirroring each other on some level, with Castleman Formation filling in between. But because if you were to go out in the field and measure these with a compass, these would be dipping this direction, and this would be dipping this direction, and you'd be able to put this together as an anticline. So when you create a cross section like this, you can really get a sense for what the rocks are doing. This image is another image of the Massanutten Mountain Range again. So here's the one side of that, and the other side of the mountain, Massanutten Mountain, and these young rocks in the middle. This is drawn by a friend of mine, Callan Bentley. But you can see the nature of the folds in the rock, which were all originally horizontal, but now have been quite folded because of the formation of Pangea. And of course, the Appalachian Mountains may extend to where they do to the south and northern Alabama, but they actually continue on through the south and up through northern Mississippi and up in Oklahoma and even into Texas as the Ouachita Mountains or the Ozark Range. The Ozarks specifically are another part of the folded mountain thrust belt folded thrust belt as a remnant of the formation of Pangea, but this time with South America getting tucked up into the Gulf of Mexico at that time. And so you can, again, see the nice linear folds. Volcanic mountains. We spent a fair amount of time looking at these, and this is kind of like this. This is the Cascades, actually. It looks a lot like Middle Earth. But there's a reason for that, because if you think about where The Lord of the Rings was filmed out in New Zealand, that is a volcanic mountain range. And so they do have that kind of character to them. So this is the Cascades, full of volcanoes and glaciers and so forth that end up shaping these mountains to look the way that they do. And of course, glaciers are a major part of this because glaciers carve out these U-shaped valleys and leave these nice arêtes or peaks up here at the tops of these mountains. But to get this, of course, you have to have subduction going on. And a subduction zone situation where the lithosphere is diving beneath the oceanic lithosphere, in this case, is diving beneath the continental lithosphere. Again, you'll get the partial melting in the volcanoes, and the character of the mountains will form because of that. Another example is the Andes, and here you have the Atacama desert area, followed to its west, actually, or east, I'm sorry. This is to the east. The west is behind the photographer and to the right. But you have these nice volcanic mountains with this desert on the eastern side, the western side, getting turned around here. So here's the Pacific Ocean. This is western South America. Pacific Ocean. Here's the Atacama Bench. And we're looking at the present day and the current Western Cordillera, which is basically the term for mountain belt, runs up and down South America. So you can see with 30 million years ago, the Western Cordillera was not nearly as big, as tall as it is today. It was maybe 2.5 kilometers. Now it's actually grown by 2 kilometers in the course of 30 million years. It's pretty amazing according to this figure. But you're looking at the desert that exists right off of the coastal scarp, and that's pretty typical of the situation. It's a rain shadow desert, so in this particular area of Chile anyway, the rains are coming from the other direction. So you get this desert on the coast. And finally, domed mountains. This is an image of the Black Hills, and it's a very, very weathered igneous materials, and it basically looks a lot like this. Basically, it's a giant lava dome is what it is, and an intrusion, igneous intrusion, where you had sedimentary rocks on top, the dome upwelled, and then the sedimentary rocks eroded, and it exposed, of course, everything. And the oldest materials are always in the center of a dome. So if you look at the cross section, here's your granite and your schist on both sides, overtopped by the limestone, and there's some nice caves actually in this limestone, and then of course the Dakota sandstone on the outer rim. And here's another way of looking at it. So we have the crystalline rocks here in the middle of this dome, the volcanic materials with the sedimentary materials on both sides. Okay, that's going to finish that up. So for the rest of this material, this week is just going to be a virtual field experience. So you'll just complete that virtual field experience, and we will reconvene on Monday.